It's just like Twitter.
Okay, good afternoon, everyone. So we're going to get started. So again, it's my pleasure to give a guest lecture. And then today's topic is going to be deep reinforcement learning. Okay, so I'll first give an introduction to reinforcement learning. And then I will exemplify what we're going to talk about with AlphaGo, which is this famous computer program that DeepMind designed to essentially master the game of computer Go and in fact beat some of the best human players from around the world. Okay, so some of this work that I'm going to talk about is actually coming from a paper that was published in Nature. So you've got the reference here. And then so later on, if you want to check this out, then that's what I would recommend. Okay, so first, let's go back to what is machine learning. And I'm assuming that in this course, since it's a course about deep learning, then you've seen already plenty of techniques, and most of them are probably falling under supervised learning. What this means is that we've got a teacher that essentially tells the learner what it needs to learn, and then more practically, you have some data, typically the input, and then you also have the outputs. You have both the X and the Y. And then essentially because the answer is already provided, so you've got the Y, then you can learn from this, and it's much easier. Okay, at the other extreme, we also have unsupervised learning, where we only have the inputs. We don't know what the output should be. We don't have the Y. And this typically happens in the context of clustering, or if we're trying to do some form of just data modeling. So this happens essentially in natural language processing, also computer vision, if you want to come up with generative models. So this would be often the case. Now, in between, we have also reinforcement learning, where in this case, the environment does not provide the answer as in supervised learning, but it still provides something, so it's not unsupervised completely. So there's some information, and then this information is going to be in the form of some hints that we're going to call rewards, or depending on the literature, it might also be called costs. Okay? But the idea is that these hints are going to provide feedback that will essentially tell the learner whether what it's doing might be good or might be bad, but it doesn't tell it what is the actual answer. Okay, so that's why it's a weaker form. It's in between, but as a result, it's quite flexible, and then you can tackle some really complex tasks. Okay, so in more detail, what is reinforcement learning? So we can define it as a process by which we're learning to maximize a numerical reward signal. And then again, as I was saying before, this numerical signal is simply some piece of feedback. It does not tell us what is the correct actions. It's just giving us some information that we can still leverage. Okay, so where does the name come from? So reinforcement learning actually comes from animal psychology. So it's been well known for a long time that you can train animals to perform various tricks, or otherwise to to do certain tasks, and often you can get them to do those things by some reinforcements. And then in the case of animals, okay, some of the reinforcements might be some form of pain or hunger. And then in terms of, so in terms of negative reinforcement, it might be pain or hunger, but you might also have some positive reinforcements where it's going to be some form of pleasure or food. And then so you can get a mouse to essentially go into a maze and reach a certain location where it can find some food, as opposed to another location where it might get an electrical shock, for instance. Okay? In general, I mean, even if we're not talking about mice, I mean, you might have a pet at home, and then you can train it maybe to perform certain things, and then again, you might use some form of reinforcement. So here, the idea is that we're going to do something similar with a computer, and then, okay, in the case of the computer, I mean, we're not going to provide food, and we're not going to provide pain or anything like this, but we can use numerical signals where internally inside the computer, it's going to have an optimization problem where it's going to try to maximize the sum of those numerical signals, and that's what's going to drive the learning. Any questions so far? Okay, good. So this should be fairly straightforward. Now, there's lots of examples where reinforcement learning can be used and has been used. So today I'm going to talk about the game of Go. So in terms of playing games where there's a sequence of actions, there's some uncertainty, then reinforcement learning becomes very useful. But then in terms of industrial applications, there's lots of examples starting in operations research. So in fact, reinforcement learning is really a framework that is derived from Markov decision processes that were proposed in the 1950s in operations research, and it has been used in all kinds of applications. So for instance, pricing techniques on the web or even just with airlines might be using some form of reinforcement learning. Vehicle routing is another one. Also, elevator scheduling, control of vehicles, and there was a famous example where Andrew Ng many years ago was able to get a helicopter to perform certain maneuvers and enter that helicopter into a contest where it essentially outperformed human pilots in terms of doing those maneuvers. And it was all done through reinforcement learning. A topic that is very important today are dialogue systems. So if you've got an iPhone, then Siri is one of the classic examples where you can use various forms of learning to get the computer to understand and even respond. I'm not entirely sure to what extent reinforcement learning is used within Siri, but in general it is a framework that has been used by various companies to perform certain tasks with respect to dialogue systems. Data center energy optimization. So recently I was talking with some researchers at Google who were telling me that internally they are optimizing their data centers because they consume a lot of energy. It is one of the major sources of cost, and then this is now done by reinforcement learning. Also, there's a lot of interest with networking companies to also develop self-managing network systems. So networks today, well, historically were mostly hardware. Now there are software-defined networks where essentially a lot of the control has come out of the hardware into a software layer. And then you've got lots of sensors that can inform you about different statistics regarding the performance of your network. And then you can optimize the parameters. And then reinforcement learning is one of the techniques that is also being investigated for this use. So in any case, there's lots of potential. And, but again, today I'm going to focus mostly on the first one. But if time could permit, I mean, we could do one lecture on each one of those applications. OK, so if we want to define reinforcement learning more concretely, a classic diagram works as follows, where you have an agent. So this agent is a computer program that's going to essentially select some actions. So these actions, in the case of a game, might be selecting the next move. If it's in a data center in terms of optimizing energy, then it might be various controls with respect to different parts of a system that regulates the temperature, ventilation, and so on. And then the environment is going to be affected by this choice of action. So here, if it's a game, then when you select a move, then perhaps there's a board configuration that changes as a result of that. And now, as part of the environment, there would be an opponent who is going to play and then change that as well. And then you get to observe what is the current state of the environment after that. And then with that observation, typically, there's a numerical signal that we can define that will tell us how good is the state of the environment. So here, the idea is that in this framework, right, the agent is trying to select actions that will influence the environment so that the environment moves into a state that is good for the agent. So the rewards are essentially numerical signals that simply tell us how good those states are. And then the agent will simply try to select actions that will get the environment into good states overall. And when I say good states overall, there are many ways in which we could measure the overall goodness. But one classic approach is that we can simply add up some rewards at every time step, and then we can add them up while multiplying them by a discount factor. So here gamma is a number between 0 and 1 that would essentially discount future rewards so that we pay more attention to immediate rewards and then less attention to rewards later in the future. Okay? So this is one framework. It's not the only framework. Right? So there are other ways of combining rewards, but this is a very popular way of doing it. Okay, so to summarize, then you see there's this feedback loop here where the agent is going to select actions that will influence the environment. Then the environment is going to reveal what is the current, what is its current state, and then also provide a numerical measure that indicates how good that was. And then the agent will presumably select an action at every step, and then this will influence the next state, obtain a reward, and then we simply want to maximize the sum of those rewards, perhaps with a discount factor. Okay, any questions regarding this? Yes?
You said that you discount the rewards which are in the future, right?
Yeah.
So is that particular for a particular type of application? Because there are certain, I guess, games you can call it that would allow you to make a sacrifice right now in order to attain a better state at the end.
Yes, yes, yeah, that's a good point. So here the discount factor is actually something that is quite common, and the intuition behind this is that, let's say we're in an industrial setting where perhaps our rewards are going to be money, but then there's an inflation rate that essentially makes it so that, you know, a $10 that you receive today is actually worth more than a $10 that you receive, let's say, 5 years from now, because in 5 years with $10 you just can't buy as much stuff as today. So there's a natural discounting that happens. And then, so based on this, there's lots of industrial problems where it actually makes sense to do to include a discount factor. But then you're absolutely right that in some other situations like games, there's no notion of discounting. So the ultimate goal is to win, and then if you can sacrifice something now so that you can actually win later on, then by all means that's a very good approach. And then we'll see in fact that for the game of Go, we will not use a discount factor. Yeah.
Okay, in the inflation example that you gave, then gamma is not constrained to be less than 1, right? Necessarily.
Well, so okay, here, yes, it is constrained to be less than 1, but I guess it depends how we interpret it here. Okay, so here, the gamma is used, it is not strictly speaking an inflation rate, but it's actually called a discounting rate that reflects the fact that due to inflation, right, then a same amount of money in the future just doesn't allow you to buy as much. So in terms of actual value, right, then we need to discount to reflect the correct value in the future. Yeah.
I was going to add that I think you've mentioned in the past that the discount rate was necessary to make the problem tractable, but I guess if Go doesn't have a discount rate, then that's not completely.
Okay, so a discount rate is also useful from a computational perspective whenever we consider infinite horizon domains, because if I add up a number of rewards, but that number of rewards is infinite, right, then I'm going to presumably get a sum that's going to be infinitely large, and then it's difficult to do computation based on this. But then if the discount factor is less than 1, then even though I have an infinite number of sums, this will be a geometric series, right? And then the sum will be finite, and this is a nice property. So beyond inflation, I guess another reason that is simply a practical reason or a computational reason, then people will often use a discount factor. But then if you don't have an infinite horizon, and instead it's a finite horizon, so there's going to be an end, there's a maximum number of steps, then you don't have to worry about anything becoming infinite. And then at that point, there's no practical reason for using a discount factor. It's only if it would make sense. So often in games, then there's going to be an end. I mean, the number of moves might actually be quite large, but it won't be infinite. And that's the reason for sometimes not using any discount factor. Yeah?
then if it's infinitely large, right? Gamma is between 0 and 1. So the powers of gamma just keep increasing. So at a particular point of time, you can approximate gamma to the power of, say, n to 0. And anything after that is also 0.
Yes, so yeah, that's a good point too. So whenever you use a discount factor like this, you could say that there's an effective horizon where after a certain number of steps, indeed, the rewards are discounted so much that they're effectively 0. So it's an interesting thing because it's still an infinite horizon, but effectively, we've implicitly kind of bounded the horizon. I mean, it's not a hard bound, right? Because I mean, it's still infinite, but effectively, like you could say that anything after a certain number of steps, right, is going to be so small that it's negligible, and you could ignore it. Yeah. And here, just for completeness, for the infinite horizon case, another approach would be to take the average, right? And there would not be any problem of infinite computation. So that's another common approach, okay? But that's beyond the scope of this lecture. Okay. Any other questions? Yes?
So in the action reward loop, is the action at every point in time decided based on the local state of environment and reward at that time, or does it do some sort of an enumeration of the possibilities in future and take that into account as well?
Yes. Okay. So yeah. So here, if the state, if the information provided by the environment reveals the complete state of the environment, then we can show mathematically that this is going to be a Markov decision process that satisfies a Markovian property, and as a result, the last state is sufficient to predict everything that will happen in the future. And then as a result, you can choose your next action just based on that last state, and that's sufficient. Now, more generally, the environment will not always reveal the entire state, so the state will be partially observable, and then it will be useful to consider many of those past observations to perhaps obtain as much information beyond just the last observation, and then it's going to be a lot more complex. And these are known as partially observable Markov decision processes. But we won't cover that in today's lecture. Yeah. Okay. All right. So these were a good set of questions, but let's keep going. Okay. So with what I've defined now, so reinforcement learning, as I mentioned before, is essentially based on the theory of Markov decision processes. So underlying a reinforcement learning problem, there is always a Markov decision process. I'm not going to go into the details of Markov decision processes, but what is important to know, at least just for today's lecture, is that there's going to be a set of states. It can be discrete, it could be continuous. There's going to be a set of actions. Again, these could be discrete or continuous. And furthermore, we could allow the agent to select actions in a stochastic fashion, so that when it makes a choice, it's essentially randomizing by perhaps using a dice or some other random number generator. Okay, so we can have actions that are selected in a stochastic fashion. We also have some rewards. These are going to be numerical signals. They're real numbers in general. And then those rewards might not occur right after each action. So sometimes they might get delayed, or at least the rewards that is associated with an action might only reveal itself much later. Okay, so this could happen too. But in any case, these are the main three components. We're going to have states, we're going to have actions, and we're going to have rewards. Okay, so to make things concrete, here's a toy example that is from robotics and quite interesting. So let's say that we've got a cart, and the cart is on a plane like this, and then what the cart needs to do is to balance a pole. Okay, so the stick here is a pole that can essentially fall down. Right, so the pole is just attached to the cart with a hinge, right, and then due to gravity, right, unless the pole is well balanced, it will naturally fall down. So what the cart needs to do is to essentially move right or left to essentially try to preserve the pole into a standing position. Okay, so this is a simple toy problem from robotics. And then historically, the way it was solved is that you'd work out all the physics behind this problem and come up with all kinds of equations and then derive some controls for this and eventually arrive at a policy that would determine when you would move right or left. But as humans, you might have at some point played where you have a stick, you put it in your palm, and then you simply try to balance, right? And you're not solving any mathematical equations, you're not doing physics, at least not explicitly, right? And somehow you're able to eventually learn how to balance the pole. So an interesting question then is, can we get a computer to do the same, right, without understanding all the laws of physics, but simply by trial and error, just like what humans would do? And then the answer here is that we can use reinforcement learning to get a cart like this to balance the pole. And here we can formulate the problem by saying that at any point in time, the cart is going to receive information that would indicate the position of the pole, the velocity of the pole, the angle of the pole, and then the angular velocity of the pole. Okay? So at any point in time, it receives this information, and then it will select an action that will be a force in one direction or the other direction. And then it will receive a reward that will be 1 whenever the pole is still standing and it hasn't fallen yet. Once it falls, then it's over. Okay? So here it will try to essentially select some actions that will keep the pole balanced as long as possible. And now, can we get this cart to learn over time to obtain a good policy? So here, finding a policy is going to be essentially a mapping from states to actions. Okay? Our states are defined up there. So again, position, velocity, angle, and angular velocity. Right? And then we're going to map this. This is a continuous space to actions. And here the actions could be simply a binary action of saying move right or move left that is enabled through a force in one or the other direction. Okay, so let me show you now a video. Okay, so this is a YouTube video here where somebody use reinforcement learning to solve this problem. Okay, and then they in fact use a neural network. Oh, okay, it's not showing on yours. Wait a second. Okay. Okay, here we go. Okay, so in this video you'll see the pole, and so somebody wrote some code, and then each time you see it moves the cart, and then it often falls, but then eventually it succeeds in terms of balancing the pole, and then you see that, I mean, it's balanced, but it still has to keep on moving because gravity eventually pulls it down one way or the other. Okay? So let's stop this. Okay, so yeah, so this gives you a concrete idea of what's going on. Okay, now the question is, how can we get the pole, or how can we get the cart to learn a good policy as we saw in the video? Oops, okay. All right, so to do policy optimization, there's lots of techniques that one can use. The most classic techniques are what are known as value-based techniques. So the idea is that, you see, we're trying to maximize the sum of rewards. So here we can define a value function. So it's a mapping from state to the sum of the rewards, where here the sum of the rewards is essentially the sum of the rewards discounted. But then those rewards depend on the policy, and then they also depend on some transition function in the environment to see how the state is going to evolve. So here I'm simply going to write the expectation of that reward based on the current state and the current action. Okay? So the objective is essentially to try to find a policy that gives us the best value function like this. And once we have a good value function, then there are ways in which we can extract a policy delta. And then one very common algorithm for doing this that you might have heard about is called Q-learning. But then there's lots of other algorithms. And I mean, there's a whole literature that goes back 30 years at least on value-based techniques. Now for this lecture, I'm going to talk about another set of techniques that are known as policy search techniques. So in their case, what they do is that we search directly in the space of policies for a representation of the policy that would directly maximize the value function. So I guess the difference is that in policy search techniques, we work directly with a representation of the policy, and then we try to adjust this definition of the policy until we obtain a policy that gives us high rewards. Whereas in the value-based techniques, we don't have an explicit representation for the policy. Instead, we're simply trying to see what might be a good value function, and once we have that, then we recover a policy. Okay, again, I will focus only on this set of techniques for this lecture, just in the interest of time. And in particular, the technique that we're going to cover today is known as policy gradient. Okay, so the reason why policy gradient is a good way to start is simply because if you're already familiar with supervised learning, we're going to see in a moment that a policy gradient technique is actually just one small tweak compared to supervised learning. So if we were able to get the correct action at any point in time, then we could use supervised learning. And here we could consider, let's say, a space of stochastic policies that would be defined as the probability of actions given each state, parameterized by some weights W. Okay? And here, this function can be represented in any way. And I mean, for the purpose of this lecture, let's just assume that this is going to be represented by a deep neural network. Okay, so here, the idea is that we have as input the state, and then we have now a network, and then there's going to be a layer at the top where it's going to produce the probability for, let's say, action 1, the probability for action 2, and so on. Okay, so let's assume here that we've got a neural network that takes as input the states. It can be a convolutional neural network. It can be any type of network. And then at the top, there's going to be, let's say, a softmax layer that will give us a distribution over possible actions. Okay, so if we've got this, and let's say that now we have some data where somehow somebody was able to tell us what is the optimal action for every state. So this would be the supervised setting. We're going to relax this soon, but for now, let's say that somebody tells us what is the best action in every state. If we have this, then we could train our policy simply by maximizing the likelihood of the data. So here we could maximize the likelihood of selecting the correct action in each state. And we can do this simply by maximizing the sum of the log of the probabilities of each action given each state. Okay? So then in a representation, let's say with a deep neural network like this, right, then you could use simply gradient descent, use some form of automatic differentiation to figure out what would be the gradient, and then adjust the weights in your network so that over time, right, it will converge towards having a high probability for the correct action in each state. So the gradient update would simply be this equation that many platforms, whether it's TensorFlow, PyTorch, and so on, can compute for you automatically. Yes?
Sorry, the value, the value function seems to have disappeared here.
Yeah, so here, okay, I just took a step back and said, let's just see again how supervised learning works, okay? So in supervised learning, there's no notion of value function because we are told what is the correct action, and this is what we would do if we could somehow just find out what is the correct action in every state. Okay, so now let's consider reinforcement learning, where again we consider a stochastic policy. Let's say it's represented by a deep neural network in the same way. Okay, but the difference is that now we get triples of state, action, reward. And here you'll notice that even though I get an action, this is not necessarily the optimal action. Right, so on the previous slide, when I use A star, it means that this is the optimal action. Here, I just means that this is some action. And then with it, we have a reward that indicates how good this action is. Okay? So this is a relaxation of the problem. It's more general because now I can get state actions where it can be any actions and then a corresponding signal. Okay, so with this, we can also do some form of gradient descent. So we're going to see in a moment how we can derive this. But then now the problem that we want to optimize is going to be to find the set of weights that maximize the sum of the discounted rewards. Okay? And here again, I have an expectation with respect to the rewards because there's some stochasticity either due to the policy or otherwise due to the environment. So that's our optimization problem. And now, in this optimization problem, if we treat the weights, W, as a variable, compute the gradient, we can show that the gradient will correspond to this equation. And if you look carefully, I mean, this equation is not very different from this equation here. The main difference is just this here, where we have a gamma raised to the power of t, and then RT. Okay, so that's the only difference. So here, RT is the sum of the rewards in one trajectory. Okay, so let's say that we execute the policy and take a sequence of actions till, let's say, the end of the horizon, which might be infinite. That's why I've got an infinite sum here. Then I could sum up those rewards, and it's essentially one sample according to the execution of my policy once. Okay, so we're going to see in a moment that computing the gradient, in this case for a policy update, is very similar to supervised learning. The main difference is that we simply introduce this gamma raised to the power of t times RT. Okay, so how do we explain this? So there's a theorem known as the gradient policy theorem, where we can show that if we want to compute the gradient of the value function for a policy parameterized by W, it corresponds to this equation, where this equation is essentially saying that the overall value of the policy comes from the stationary distribution of the states when we execute the policy for a long time, times here the probability of choosing actions in each state, times here the value of the policy when we're in a certain state, execute the action, and then follow the policy thereafter. Okay, so I guess the two things that I've introduced in this theorem that were not defined previously is this notion of a stationary state distribution, and then also a discounted sum of rewards when we start in state S, execute action A, and then follow the policy parameterized by W thereafter. Okay? So, okay, so I'm going to show you now the derivation for this theorem. And to be honest, normally I would need more than one lecture to really explain in details where does that stationary distribution come from and where does that Q function come from. So for now, I've given you I guess, a definition in words. I'm going to leave it at that. We're simply going to use those terms now to do the derivation. But yeah, it would take more than a lecture to explain this. Okay, so this theorem can be derived with this set of equations. I'm not going to bother explaining all those steps. They're essentially just rewritings that take advantage of what is the definition of each of those terms. And then, yeah, at the end, we arrive at the statement of the theorem. So that shows that essentially computing the gradient can be decomposed in this fashion. And now we can further rewrite this, where the gradient can be rewritten in the form of some expectation. And now we can sample just one term in this expectation, which is going to give us essentially a sample gradient for doing stochastic gradient descent. Okay, so then in my previous slides, when I explained how we could do a gradient update with respect to a policy, I was using this term here, and this is the derivation that you need to obtain that. Okay. Yeah, so I guess, yeah, the key again is that we've got some definition in terms of terms like the Q function and then the stationary policy, the stationary state distribution. And then beyond that, after that, then we're simply going to take one sample from an expectation here that will give us this term. And that's what we can use then to do an update based on one trajectory when you execute the policy. Okay, so this is a beautiful result, and then it led to this algorithm that is actually called reinforce. Okay, so it's not the only reinforcement learning algorithm, but when it was proposed, this was back in 1992, there were not so many algorithms for reinforcement learning, and I guess at the time somebody figured I might as well call my algorithm reinforce, and that's the name it got. And so it's quite clear that this is going to be for reinforcement learning. And then it is, in fact, one of the most popular algorithms still today for policy gradient techniques. It is often the base of most policy gradient techniques. So there's lots of variants on this, but that's essentially the base, or like the most common approach. Yes?
This stochastic gradient cannot be applied online, yeah?
So it cannot be applied on?
Online. For example, after each step in a trajectory, we want to update
Sure, you can do that, yeah.
RT is...
Oh, okay, right. So yeah, here RT is the sum of all the rewards we would get till the end of the horizon. So I guess, yeah, this would work in the context of episodic problems, where, for instance, in the case of games, then this would be the sum of the rewards till the end of the game. So you could think of every game as one episode, and then so you could learn based on this. But then, yeah, within one game, then we would have to come up with a variant for this, and then there are ways in which we could do some updates after every single actions. But yeah, for the purpose of this lecture, we're just going to go with this basic form. Yeah. Okay. All right, so now let me go on with the example of AlphaGo, and we're going to see how this reinforced algorithm is indeed used in AlphaGo and was a key component. Okay, so let me first introduce the game of Go. So it's a popular game, especially in Asia, and it is a very complex game. Although when we describe the rules, it's a very simple game to describe. So here I've got the rules where we've got two players, black and white. And then what they do is that they alternate in terms of placing a stone, either a black stone or a white stone, at one of the intersections on the board. When they place a stone at one intersection, then after each move, we're going to check if there are some stones that do not have any liberty, where here liberty simply means that there would be an empty intersection adjacent to that stone or adjacent to the neighbors of that stone. So, for instance, if we have a set of connected stones of all the same color and none of them has a liberty, so an adjacent intersection that is free, then they would essentially be surrounded and captured, and therefore they would be removed from the board. So that's essentially how the game goes, that everybody puts down one stone, one after the other. Whenever some stones are surrounded, then we remove them, they're essentially captured, and we keep on going like this until at some point in time where both players would agree on what region is being controlled by which player. So for instance here, we could perhaps see that there's a big region that is controlled by black, because black essentially is surrounding this region. And then we would essentially count all the stones of each player and then the regions that they control to determine the score. Okay? So that's at a high level. There are actually a few additional rules that are important in the game, but at least these are the main rules. Okay? And that's really what you need to know at this point. Any questions about this? Okay, good. So this game, despite the fact that the rules are very simple, is actually very complex. It is much more complex than chess, for instance. And in terms of getting a computer to play this game, so there was a lot of work for decades, and it was only in 2015 that there was a major breakthrough in terms of achieving a level of play that was comparable to humans. Okay, so in 2015, the state of the art was that we had a bunch of other computer programs to play Go. So GNU Go, Fuego, Patchy, Zen, Crazy Stone. And then they achieved a performance that was okay, in the sense that in some cases they would beat beginners and then they could match some amateurs. Okay? So here this is a scale for ranking players, and then higher is better. And then in Europe, there was an expert player. His name was Fan Hui. So according to this scale, so he was a professional player with 3 dan, roughly. Okay, so that's the green column. And then in 2015, Google DeepMind designed AlphaGo. And AlphaGo essentially matched and eventually exceeded Fan Hui. Okay, so there was several matches that were performed between AlphaGo and Fan Hui, and eventually AlphaGo, I believe, won 4 out of those 5 matches. Okay, so what happened here? So how did AlphaGo become better than one of the top player, at least the top player in Europe, and also, totally beat these other computer programs? So those previous programs were essentially using Monte Carlo tree search. So Monte Carlo tree search is another technique that is also used within reinforcement learning, and we're going to see, in fact, that AlphaGo does use Monte Carlo technique too, but not just that. It also uses policy gradient update that we're going to see again in a moment. But in any case, yeah, Monte Carlo tree search was good, but not sufficient to achieve professional play. And then with deep reinforcement learning, then AlphaGo was able to really break out and beat Fan Hui. Okay, so this was October 2015. And then in March 2016, AlphaGo beat another top player. His name was Lee Sedol. He was ranked 9 dan. So if I just go back, so you see 9 dan would be at the top of this scale. So he was one of the top players, but not the top player. And at the time, the world champion, Kedje, made the following comment on social media. So he claimed that AlphaGo cannot beat him. But then in 2017, there was a match between him and AlphaGo. And sure enough, AlphaGo defeated him. And then at that point, he wrote, well, last year, AlphaGo was still quite human-like when it played. But this year, it became like a god of Go. Okay, so at this point, AlphaGo is the uncontested program for playing Go, and it has been able to defeat the top human players of the game. Okay, so how did it do this? So the strategy, there were 4 steps. So first, they used supervised learning to train some policy networks to essentially imitate the professional players. But then just imitating the professional players does not mean that you're going to beat them, right? You could get good by imitating, but at some point, if you want to surpass, you have to come up with your own strategy. So this is where reinforcement learning came in. And then reinforcement learning was used to learn both policy networks and value networks. And then they were combined afterwards into a Monte Carlo tree search technique. And I'm going to explain those 4 steps. Okay, so first, the policy network was essentially a deep convolutional neural network where as input we have a state, and then the state is essentially a board configuration. So we saw earlier that a board configuration is essentially a grid that's 19 by 19, and then each intersection might be occupied by a white stone, a black stone, or simply free. Right? So we take as input essentially a board configuration, and then we have a multi-layer neural network that essentially applies convolutions and then recognizes patterns, and then at the top will produce a distribution over the next action. And here the next action is essentially placing the next stone at some free intersection. Right? So every intersection that is free is a possible action, and then it would have a distribution over that. Okay, so that's the policy network. And then it was trained initially to imitate some of the Go experts based on a database that contained 30 million board configurations. And so there's a server called the KGS Go server that contains this database, and then it was used to train this neural network. Yeah?
Would that make sense using a Marian-Man in that case, since it's a sequential training? Or?
Oh, certainly, yeah. Okay, so I guess what I'm doing now is I'm just going through the explanation of how AlphaGo was designed. So there was no recurrent neural network used in AlphaGo, but, or at least I'm not aware of it. So what I'm describing, in fact, is the implementation that was used in 2015 to defeat Fan Hui. Now, I do not know the details of what changed for 2016, 2017. And then the state of the art now in reinforcement learning, many of the techniques do use recurrent neural networks. Okay, but again, since we only have 1 lecture, we won't have time to go through those details. And we're just going to stick to what was implemented in AlphaGo. Okay, so all right, so yeah, so it was trained with the KGS Go server, and then so it essentially imitated, and it was able to obtain some reasonable policy. Okay, so yeah, to do the training, again here, this is a form of supervised learning, because in the database, there's some Go experts that essentially agreed on what is the optimal action at each one of those board configurations. Okay, so then we simply apply well, we don't need to use reinforcement learning, just supervised learning here. And then so we can define the gradient to be essentially the gradient of the log of the probability of that best action in each state. And then we can update the weights of our neural network simply with this. Yeah?
And there are a lot of states that you should be able to consider for the 19 class.
Oh yes, there's lots of states, because yeah, the board itself is 19 by 19, so that's 361. Now each one of those intersections might have a white stone, a black stone, or might be free, right? So it means that overall there could be roughly 3 to the 361, and so that's a huge number. And obviously here, even though they had 30 million board configuration, this is just a tiny fraction of the entire state space. So this is where machine learning is very useful, because it can generalize from a set of examples, right? So here we only have a tiny fraction. From this it will learn presumably some strategies, and then it can extrapolate so that when it is given a new board configuration, it will select an action that hopefully is going to be good, that will correspond more or less to some strategy that can be inferred from this entire database. Yeah.
I'm just wondering, but so the fact is, I mean, they were lucky that there were a bunch of players who agreed what was optimal, right? But if you try to transfer this to other domains, then you don't have access to, I mean, there's optimal actions that you can't use this, right?
Right. Yeah. Okay. Yeah. No, that's a good point. But we'll see in a moment that they didn't stop there. I mean, this gave them a policy that in fact was not that great. It was still a good policy, but then reinforcement learning had to be used. And here this was essentially a way to kind of start with a reasonable policy so that we don't have to learn from scratch. So it was essentially helping in terms of cutting down the amount of learning time. Yeah. Okay. Right, so now, okay, once they obtain the policy network by supervised learning, then in order to surpass those experts, then the network needed to be able to learn its own policy, and then it was through reinforcement learning that this was done, where they used the reinforced algorithm that I explained earlier. Okay, so then again you compute a gradient. The main difference is that you see now the gradient is not just the partial derivative of the log of the probability of the action given the current state. It's also multiplied by the discount factor and then the sum of the rewards for that particular game. Okay. Now here the intuition is that you see if you play a game and you're not told what is the optimal action, so you simply choose an action at every step, right? Then there's no reason why you would like to compute a gradient that would try to help improve the probability of choosing that action again. You would only want to do this if this is an action that leads to, I guess, a high reward. So that's why you see by multiplying by RT, right, we're essentially scaling the gradient in a way that will make it more important if this is going to lead to a win where you get a high reward, and then if it's going to lead to a loss, then it's going to have a small gradient, and in fact here you might have a negative gradient if you define a loss as a negative reward. Okay, so then it will adjust the weights in such a way where by taking into account the rewards, then it does the change in the right direction. Okay, so that's the intuition. Okay, so in this case, for each game, if it's a win, then RT is going to be equal to 1. If it's a loss, RT is equal to -1. Okay, so then going back, you see this makes sense. If it's going to be a win, it means that this action presumably was very good. I mean, we don't know if it was optimal. Maybe you could win by a bigger margin. So in the game of Go, I guess you can count your stones versus the stones of the opponent, and then you can win by bigger or smaller margins. But if we ignore that, if we just care about winning, period, right, then here, I guess we can just have this equal to 1 or -1, and then we're going to assume that if it's a win, then this action was as good as any other action, and therefore it's kind of like optimal, and then this would correspond to the same as doing supervised learning. But if it's a loss, then it will take a step in the opposite direction of the gradient because it's going to multiply by -1, and then it would try to essentially decrease the probability of that action. Okay, so also for the discount factor, then it was set to 1 because here the game will eventually end, so then there's no need really for discounting. So based on the discussion that we had earlier, it was not needed, so they use a discount factor of 1. So effectively, this was the gradient that was used. Okay. All right, so yeah.
Train this, for example, could we have another neural network to decide for a particular action if I can set the discount at that time based on my actions? It would provide the best counter action based on the current state.
Right, okay, yeah, I guess, yeah, I did not explain how it was, like, how did it play a game. So essentially it played games against itself. So here, I guess, yeah, we're optimizing one policy given an opponent that uses the same policy, but where that policy, let's say, is fixed. Okay, so it's essentially playing against itself, and yeah, so then it would essentially try to improve with respect to its current policy. That's effectively what this does. Yeah. Now here there's a danger when you play against yourself like this. You might have a policy, then you improve in a certain way, but then after that you might get into a cycle where essentially coming up with sequences of policies that are always better than the other one, but then you're never really improving overall. So to counter this, when they play against, when you get the computer to play against itself, they store all the previous policies so that this way it's trying to improve with respect to all the previous policies, and then it's a lot harder to get stuck in one of those vicious circles so that it can improve with respect to everything that it comes up with.
So it chooses the policy based on whatever policy it used before.
Exactly, yeah. Yes?
The only place that deep learning comes to play is this function estimator from state to action, right? Is there any other part of the algorithm that deep learning?
Okay, so yeah, so far I talked about the policy network, but then on the next slide we're going to have a value network as well. So there's essentially two deep neural networks, one that corresponds to the policy, the other one to the value function. Yeah, and then in both cases, I believe they use some form of convolutional neural networks. Yeah.
I mean, my point is that it's essentially, I mean, what we call deep reinforcement learning, essentially is reinforcement learning, except that function estimators are deep learning.
Yes, that's right. So yeah, deep reinforcement learning is just reinforcement learning where the function approximator is a deep neural network as opposed to some other function approximator. Yeah, yeah. Okay, so yeah, the next thing that they did is they also trained a value network where the value network would essentially try to predict whether from a certain board configuration, when you apply a policy, whether that policy is going to win or lose. So you see the way we define the rewards is that there's a +1 for winning, -1 for losing. So now when we train a value network, so at the end, it produces one number, and that number is going to be a number between -1 and +1. If it's close to +1, it means win. If it's close to -1, it means lose. Okay? So then it'll try to predict in this fashion who's going to win. And yeah, so this was trained essentially by minimizing the Euclidean distance between what the value network currently generates and what is the outcome of the game. Okay, so again, they get a network to play against previous versions of itself, and then if it wins, this is going to be +1. If it loses, this is going to be -1, and then it simply tries to minimize the Euclidean distance between those two. Okay, so again, this is just applying deep neural networks where you train to minimize Euclidean distance in this case. Okay, and then finally what they did is they combined value networks and policy networks through a Monte Carlo tree search technique. So the way this works is that, well, okay, with the policy network, at any point in time, you could simply follow the policy network and choose an action. Or you could also look at your value network and try to consider every single action and then see if you end up into a state where you're going to win or lose, and then based on that select again the action that would lead you to something where you're going to win. So you could use either one. But now especially with this approach with the value network where you could just simulate one step, see where you end up, and then predict from that point on whether you're going to win or lose. You don't have to just do one step. You could actually simulate multiple steps, and then the more or the deeper you do your simulation, right, then the more accurate this is going to be because you only have to make a prediction much later after many steps. Right? So the traditional approach, in fact, for getting a computer to play a game is that you do a simulation where you are in a certain state, you simulate what would happen for every possible move up to a certain depth, and then either you go all the way down to the end or you stop early and then you do an approximation, you make a guess about what's going to happen for the rest of the game. So here they use this approach to improve because if you can simply delay the predictions that you need to make till after a few steps, then at least those few steps are going to be correct, hopefully, and then so you can obtain a better policy overall. Okay, so Monte Carlo tree search is an approach to expand the search tree in a way where it will expand mostly the part of the tree that is likely to lead to a good policy. The problem with Go is that you see there's lots of possible actions. So when we start expanding the search tree, let's say that this is our current state and now we're considering all possible actions. Well, here in this graph I've only considered two possible actions, so I can put a stone here or I can also put a stone up there, right? So these are two possible actions, but now again if I consider the entire board, there's 19 by 19 intersections, 361 of them, so I might have like hundreds of possible moves, right? So here this layer, right, could have hundreds of possible configurations. And then every layer, as I go deeper, right, you increase the number of possible configurations by a factor that is in the hundreds because there's so many possible actions, right? So you clearly cannot expand everything exhaustively because it's exponential in the number of actions here, which is in the hundreds. So Monte Carlo tree search gives us a way of saying, well, let's consider the most promising actions only, and then we're going to do some simulations that will go deeper. So we're not going to consider everything. So like let's say here that there's really just two actions that are considered good. So let's expand them, and then we keep on going, and then we go deeper. And in this way, we can try to refine or spend most of our energy on the actions that are good looking as opposed to being exhaustive. Now the drawback of doing this is that unless you have a way of already pruning which actions are going to be bad that is correct, then there's a danger that you're going to think that these two actions are the most promising actions, but they turn out maybe to not be so good, and you're ignoring the best action, and then this would not work. So Monte Carlo tree search is greedy and tries to go with the most promising actions, but then there's some stochasticity in how it chooses the actions so that it will indeed in the long run consider every possible actions. But then, yeah, with this trade-off, it has formal guarantees where if you do enough simulation, you can show that in the limit, it will indeed investigate all possible moves and find the optimal one. But then in practice, it does not do that. In practice, it is more opportunistic, and that tends to work well. Yeah?
Does it fix the branching factor that it considers at each stage, or is it like an epsilon greedy sort of exploration where it could have 20 possible good, okay moves at one step, but only 2 at another?
So it's not fixed. It all depends. Okay, so we're going to see in a moment how it does the search. And the idea is that it will start with a tiny tree, that it will grow both in terms of depth and in terms of width as it does more simulations. Okay, so all right, so I guess in this tree, what should be clear is that every node is a state and every edge is an action. Okay. Now, with every edge, we're going to store the Q function, which is the sum of the rewards, and then we're going to store as well what is the probability of choosing that action according to our current policy, and then a count that tells us how many times we've chosen this action in this state. Okay, so we're going to store these three things, and then every time we do a simulation, we're going to update our count. So we just increment it by 1 for every state action pair that we visit. And now the choice of action is going to be done as follows. So whenever we're in a state and we're looking at possible children, so that means possible actions, we're going to select the action that maximizes the Q function plus a bonus defined by mu of SA. So this is an exploration bonus that's going to try to ensure that eventually we do explore lots of actions. We are not going to be stuck just with the most promising actions, which might be wrong if we don't have a good estimate to start with. And this exploration bonus is going to be proportional to the probability of choosing, okay, I think I've got a typo here. I believe this should be the probability of A given S as opposed to S given A. Okay, so it would be the probability of choosing an action given a state with our current policy, but then divided by 1 plus the number of times we've chosen that action. So the ideas that you see at the beginning is going to focus on the actions that are most likely to be chosen according to our current policy. But once it has tried many times an action that corresponds to our current policy, then it will decrease the bonus simply because it divides by this sum. Okay, so then over time it will be forced to explore gradually. Okay, and then the Q function is not defined in a traditional way. So the Q function here is going to be a weighted combination of the estimate from the value network and the estimate that comes from doing a simulation all the way till the end of the game. Okay, so Ri, again, is whether we win or lose based on completing the game, so +1 or -1. And this is the prediction based on our value network. And then so we take a weighted combination of those two. So this is really a heuristic. Okay, so lambda here is just a number between 0 and 1 to ensure that we take a convex combination of those two. And here, what this means is that we essentially take the average of all the iterations or all the previous trajectories where we essentially went through that state action pair. Okay, and then look at what were the value estimates, or otherwise the actual win or loss. Okay, so yeah, so this gives us an estimate here of the value of choosing a certain action in a certain state, and then again we augment this with the exploration bonus. So what this means is that we're going to start, right, in a certain board configuration. Then we need to choose an action. So let's say that we consider those two possible actions. So we're going to select one of those two according to the formula up there. And then if it is an action that we've chosen in the past, then it's simple. We simply go down that branch. But if it is a new action that we've never chosen before, then we create a new branch in the tree. Okay, and that's how the tree can get wider. And then we keep on going like this. We're going to reach eventually a leaf, and then at that leaf, we're going to in fact create a new child, and then so we're going to grow as well in depth in this manner. So this is a very specific variant of Monte Carlo tree search. So there's a whole literature on Monte Carlo tree search, and in any case, this is what AlphaGo used. But then presumably some of these other variants could have worked just fine too. The main thing is that this variant was using the notion of a value network in here as well as a policy network in here. Okay, so that's how I was combining both the policy and the value network. Yeah?
Do these two networks learn simultaneously, or?
Yes, so They were both learned by self-play, and then after that they were combined, and then to obtain an improved policy by doing these types of simulations. What I am not sure of, though, is I think they were trained initially through self-play, and then when Monte Carlo research was used afterwards, then they were fixed, and I think there was no training, but I'm not entirely sure. And then the Monte Carlo research was mostly used here to essentially combine them and obtain an improved policy. Yeah. Okay, so the results of applying this in some of the games that AlphaGo played with Fan Hui, so this was one of the top players in Europe, yielded the following results. So there were formal and informal games. I believe the main difference is that the informal games had shorter time control, so that means players had less time to select their next action, and it was just the formal games that were really counting in this tournament. And then we can see here who won, and so in the end, AlphaGo won 4 of the 5 games that were formal. Okay, so this completes what I wanted to present today. So to summarize, we talked about one technique, policy gradient. This technique is quite natural, especially for people who have a good background in supervised learning, because we saw that computing the gradient is just one small tweak. We compute the gradient as usual, but then we simply multiply by the sum of the rewards with respect to one trajectory. And then this was used effectively in AlphaGo. There's lots of other techniques that also use that. And there are many other techniques that do not use that. So if you want to learn more about deep reinforcement learning, so here's a plug for a course that I will be teaching next summer. So I will be teaching CS 885 deep reinforcement learning, so in spring 2018. And then we're going to cover as well deep Q networks that were quite important. Recurrent deep RL, so this answers a question that was asked earlier. We're going to talk about memory networks. In terms of applications, we're going to see how this can be used in conversational systems as well as robotics. Yeah?
The fact that we have function estimator here using deep network, just intuitively seems to me that it can be applied to some situations that can't be applied to some other situations. Say, for example, instead of Go, if we have chess. Go basically, the board has some pattern. And you can imagine that a convolutional neural network take this pattern and produce action.
Yeah.
But chess, each of these pieces are different from the other one. They have some movement. And it's not clear to me that a deep neural network can look at this board and produce an action out of that. Is
right.
there in the literature, actually, anyone tried this technique, for example, on chess, or something similar that the pattern is not that, expressive?
Mm-hmm. Yeah, that's a very good point. So yeah, here one of the key to the success of AlphaGo was that you can look at the board and then you can think of those black and white stones as just black and white pixels in an image. And then it made total sense to use a convolutional neural net, which was successful in all kinds of image recognition tasks. So I guess, the question that Ali is raising is now, if we take another game where the board does not look like a regular image, is this going to work, right? And okay, in theory, the answer is yes. So in theory, right, then the deep neural network would take as input some states, right? And then it will produce some actions. And then, so deep reinforcement learning has been used for all kinds of problems. including problems in robotics, where here the inputs might be various measures that come from accelerometers and sensors on the robot, not just video images, and then it does work as well. There, what happens is that, I guess, the neural network has to generalize in a different way, right? So it's not going to necessarily use convolutions to extract patterns in the same way that it would do in images, but the idea is that the neural network, if it can automatically come up with some good intermediate representation that correspond to features that make sense for this problem, then it will eventually be able to select the right actions. Now, the problem is that, yeah, there's still a gap in our understanding of what do those neural networks do in terms of coming up with these intermediate features, and when will it work. So we know at least that for images, then convolutional neural networks do a very good job, and they do generalize well, but then for other types of networks, or at least other types of problems that are not images, yeah, that is not always clear. I mean, still, I mean, it has been used in the context of robotics.
But in this case, chess, I guess you can even picture as the number of movements it has, right? So in this, you can represent it as black and white, whereas in chessboard, you can represent each pixel by actual value ranging between 1 and the number of movements it can make.
Right. Okay. Yeah. So here, yeah, we could still have an image-like representation if we give a numerical score to each piece, and in fact, that's often what is done in chess, because there's some heuristics for determining the value of each piece, right? And then you could just use that, and it would be interesting to see what happens. So in fact, I don't know. I'm ready to bet that somebody has tried to use a similar approach in the context of chess, but I'm not sure. And then even if somebody did, there won't be a big press release about it if it does well, simply because chess is considered solved. So just by doing an exhaustive search using classic techniques like alpha-beta pruning, then you can beat some of the best humans. So yeah, so the game has already been solved using classic techniques.
I think maybe instead of using just a vanilla convolutional network, what you can do is use something like a variational autoencoder for chess, because that way you're learning a slightly more sophisticated, hidden representation, right? So, and I think there is an approach in robotics where you can take images of the environment, use a variational encoder to do the image processing, and I think that works better. So I think you wouldn't use a vanilla convolution.
So there's plenty of things that we could do. So maybe, yeah, I know we don't have a lot of time, but let me just show you one video as well in the context of robotics. So it's a video that went viral by DeepMind. So some of you have probably seen this video. Okay. So I guess, yeah, we've got a humanoid that was trained, and it has to go under and over some obstacles. Okay, I guess these are just ads from Google. Yeah, that's pretty annoying. Okay, good, I got rid of this. Okay. It's interesting how the arm is just, up, and then there's some interesting movements that it does with it. Okay. Yeah, let me stop it. Okay, I guess, yeah, this is it for today, and thank you very much.